Hi there, guys. We're working towards 9E in the book now. This is about performing transformations on objects in the XY coordinate plane using matrices. So we're using matrices on a set of coordinate points, potentially one, potentially a set of coordinate points. But the matrix will perform a certain type of transformation. Those transformations could be reflections, rotations, there could be enlargements. There could be enlargements sort of overall from always from 0, 0 in these cases, in fact, or so in both directions, in the X and Y direction, or it could be in one direction in particular. What doesn't turn up in this exercise is translations, but translations are actually really simple to do. To essentially, you add another vector onto your coordinates written in terms of a vector as well. So that's not here, but that turns up next, and that's actually quite easy. So in example 6, they deal with some transformations here, a rotation, a reflection, and an enlargement, and a stretch in one particular direction. Again, not translations. And they deal with this without matrices. So this is just stuff from previous courses for most people. So have a look through this one. It's not what I'm going to be dealing with here. I'm dealing with essentially this and developing these matrices here. So this is given to you in the formula booklet, and I'm going to try and make some sense of all of these different transformations which we have when we apply these matrices to particular points or sets of points. Okay, right. So I've just taken some of these, and let's perhaps deal with one of the easier ones to start off with. So let's deal with maybe these things here. So the enlargements, because the enlargements are relatively straightforward. Now, let's start off with, say, for example, this one here, and let's try and apply that to a particular point in a particular example. So let's say we've got 2, 0, 0, 1, which supposedly, according to this, would be a stretch parallel to the x direction with a scale factor of 2 in our case here. So now if I applied that to the coordinate point 2, 3, which I'm writing down as a vector, okay, so that's really applying to my coordinate point 2, 3, but I'm just writing it as a vector here. Then obviously when I do that multiplication, this is a 2 by 2 matrix, and this is a 2 by 1 matrix. The matrix multiplication is possible, and we should end up with a 2 by 1 matrix. Okay, so 2 and 0 times by the 2 and 3, and then sum together gives us 4 plus 0. It's going to give us that 4 there. And then the 0, 1 times by this thing here is just going to pick up on the y coordinate there and just deliver us with that y coordinate. So the 2 and the 0 just said, well, we're not interested in the y coordinate when we times by this, but we are interested in timesing the x part of the coordinate by 2. So this is going to give us the answer 4, 3. Okay, so that's just a quick verification of this. Now, if you wanted to say, for example, then times everything by 2, so stretch in the y direction as well, well, then when you do this times by this and then sum those two things together, you'll end up getting a 6 here. And that's just a quick demonstration of this. And of course, if we put a 1 there, then we'd get the demonstration of this version as well. We just get our 2 there. Okay, so these ones here are pretty straightforward. So an x direction stretch is going to be using this matrix here, and k is going to be your stretch factor. A y direction stretch is going to be the adaptation of your normal identity matrix. So again, in the y direction, if we want to times that by 2, we'll need to use a 2 there instead. And then we can combine those two things together pretty easily by making a scale factor of k enlargement in both directions from the center 0, 0. Now, all of these stretches here are from the center 0, 0. That's all that we're dealing with from the formula booklet in terms of matrices. Okay, so stretches are pretty straightforward. Stretches that we've done. Now, in terms of reflecting in the x and y axis, that's just a little extension of these ones as well. So Say, for example, we wanted to change the coordinate point 2, 3 to the coordinate point minus 2, 3. So in other words, we're going to stretch to reflect that in the y-axis. So you've got 2, 3 is up here, and then minus 2, 3 is going to plot over here. So that's going to be a reflection about the y-axis. Now, if you wanted to do that, that's simply a horizontal stretch with a scale factor of -1. So if you want to reflect in the y-axis, you're going to need to use -1, 0, and then 0, 1. That's reflect in y-axis. Now, I would try and come up with some notes here, because I think just the formulas from the formula booklet are not going to be sufficient for you to remember all of these things. And I think it's a good idea to write some notes on all of these things. But so reflection in the y-axis, fairly straightforward. And of course, you can imagine what a reflection in the x-axis is going to be. Just similar. You're going to have a reflection in the x-axis would take the coordinate point 2, 3 to the coordinate point 2, -3. Okay, so our height of 3 would now become a height of -3. Okay, so that would be reflecting in the x-axis. This one, reflection in x-axis, worth noting down. Okay, so there's reflections done and stretches, so we've combined those things. Now, there's obviously other things here. So there's a reflection in the line of y equals tan of theta x, and I'll leave that until the end. And then there are some rotations here as well. Now, worth noting about these rotations, obviously that they're given to you, but these become much more simple if you're just going to do this in terms of 90 degrees. You know, if you put 90 degrees into cos or into sine, you're going to get out 0 or you're going to get out 1. So these matrices here are going to become much more simple when we deal with them in terms of just 90 degrees. And that's what I'm going to start with now, in fact. Okay, so now I'm going to do a rotation matrix just in 90 degrees, just to build up the formula which we're given in the formula booklet. So just to sort of spoil it, the formula in the booklet for anti-clockwise is given, and the formula in the booklet for clockwise is also given. So if you want to skip the proof of those things, by all means you can do. I think it's good at least to know how to make these, and that these are actually quite easy to make for 90 degrees though. Definitely stick in for that. That's what I would suggest, and write some notes as you go as well. Okay, after that, we'll look at this reflection matrix as well, and trying to develop that one too. But again, you can just apply that one, and these things do just exist here as well. Okay, another thing to say perhaps as well, just before I actually do this, there's actually a really nice investigation in the book, this investigation 5. I think it is worth going through this, and you will get some real understanding as you go through this one as well. Oh, good thing in this as well is when they start talking about applying a matrix, here they're saying apply the matrix 1, 0, 0, -1 to a set of points. You can write that set of points in one complete matrix there. So you can see here they've come up with A is 1, 1, B is 3, 1, and C is 2, 2. And they've just written that down in this matrix here, 1, 1, and then they've gone to C actually 2, 2, and then to B 3, 1. So they put it in a condensed matrix format. And this works in that format as well, which we can look at in a bit. But let's look at this. So this is our original point. We're talking about rotating it by 90 degrees clockwise here. So this would be 90 degrees clockwise, and rotating it by 90 degrees anti-clockwise as well. And so we are dealing with rotation matrices. That's what we're dealing with. Okay, so there's our original point, and you can see that that is 2 across and 3 up. And hopefully by a kind of L method, we rotate that L around, so like that. This rotates by 90 degrees, and this rotates by 90 degrees. You can see that we should end up in this position here if we rotate 90 degrees clockwise. Okay, so then let's write the original point as 2, 3. And we want to end up with the point 3 minus 2. So the matrix needs to give us this. So now remember, the identity matrix is like this. And so this line picks up on only the x part of the vector which we have here. The vector is how we're writing our coordinate point. So the 1 would pick up on the 2 there and would give us a 2 here, but we don't want that in this case. We actually want to pick up on the y part. So to pick up on the y part, we're going to need a 0 and a 1. We don't want the x part there. We want to take the y part. And likewise, we want to pick up on the x part for this bit here. So the x essentially becomes the y. So we're switching around the x and the y, but you'll also notice that we need the negative of the x there. So we need a minus here as well. So that was quite easy to develop, even if you do have the formulas as well. That's pretty straightforward to make up. Okay, now you can verify that with other points. If you want to apply that to this point and see that you actually get the point around here, you can do. We're only just sort of creating these. You can verify it with other ones as well if you like. But this one does always give you a rotation of 90 degrees clockwise. So this is rotation 90 degrees clockwise. Okay, well, also then on the coordinate point 2, 3, which we're writing as a vector, if we wanted to go anti-clockwise, we'd get minus 3, 2. And you can see that that's going to be really similar, just that we want the 3, the y number becoming the x number there to be negated, to take the negative of that. So in this case, this is going to be our rotation of 90 degrees anti-clockwise. Okay, so that's the matrix which we need to apply to any set of coordinate points which will take us 90 degrees anti-clockwise. Okay, well, what we're going to do next is build up to the two formulas here. So let's deal with this in terms of anti-clockwise. I'll deal with the anti-clockwise one, and the clockwise one I won't do, but obviously you can do it in a very similar way. Okay, and one other thing, just looking at this set of coordinate points here, just to confirm really that this is relatively straightforward. If you were applying, say for example, this matrix here, so this matrix again is our that's going to be a reflection. Actually, that's our reflection in the taking the y's to be negative, so it's going to be a reflection in the x-axis. So if we apply that in this case here, we can see we're going to do 1, 0 times by 1, 1. And so that's going to give us the answer of 1. And then 1, 0 times 2, 2, which is going to give us the answer of 2. 1, 0 times by 3, 1, which is going to give us the answer of 3, of course. So when we sum those things together. And this times by this and summed is going to give us minus 1, and so on. Minus 2 and minus 3. Now you can see this set of coordinate points, if you actually plotted those, it's going to give you 1 minus 1, and then 2 minus 2, and then 3 minus 1. I made a mistake there. That was minus 1. So, and then we can join those points up as well. So there we go. You can see that this is giving us our reflection in the x-axis. Sorry, I was sort of struggling with that one. I thought it was going to be a rotation there. Actually, it's a reflection. Okay, so you can see that how that applies to not just to one coordinate point, but to many coordinate points as well. Okay, so next little bit then we're trying to develop is going to be this formula here. Okay, now I'm going to need a diagram in this case, and what I'm going to do is take just a really simple x coordinate point and a really simple y coordinate point with no x involved, and then I'm going to combine those two things. So first, what I'm going to take is I'm going to say here's my coordinate point 1, 0, and I'm going to reflect this about theta. Put theta there, and it's going to go round like this, and it's going to end up here somewhere or other. I'm going to just exaggerate that right angle triangle a little bit there. And really what I want to know now is what's this new coordinate point? So I'm taking a really basic coordinate point where I'm only interested in the x component. And in a moment, I'll do that with y as well. So in order to move up to here, you can see that this coordinate point has the x distance of, in this right angle triangle, see that this is a length of 1 still, that was a length of 1 there. This whole distance, by the way, was a length of 1. Of course, that is the same length as this one here. So this is a length, the hypotenuse is 1. And what we want here is this length here. Well, that's some simple trigonometry. You know, you can set up your CAH triangle, and you can say, well, we're interested in the adjacent, so the adjacent is equal to cos of theta times by the hypotenuse. The hypotenuse is 1, so that's just going to give us cos of theta. So this is going to be the coordinate point cos of theta. And in a similar way, the height of this coordinate point is actually going to be sine of theta, which you can verify from, SOHCAHTOA, from trigonometry. So that's sine of theta. We're looking for the opposite there. We have the hypotenuse, we have the angle. Okay, so that's what happens to our coordinate point 1, 0. Now, if we were going to do that with another coordinate point here, let's say, in this case, let's take the example 0, 1. Okay, so in this case, we're only interested in a y component here. And again, if that rotates around here, we end up somewhere around here. There's our theta, there's our right angle triangle. And you can see in this case that this coordinate here has the coordinate point cos, not cos, struggling to write even here. So this is our distance across, which is the same as this height that we had here. That's just using sine. We want the opposite length in this right angle triangle. So that's sine of theta, but obviously that needs to be negative now because we're on the other side of the axis. And we want cos of theta as our height, and that's not negative at all, that's still positive. Okay, now if we combine those two things together for our anti-clockwise rotation, and if we say, well, we want to combine those to act on not just 1, 0, and not just 0, 1, but any x value and any y value. Okay, so I'm going further than even saying the coordinate point 1, 1 here. What we're going to need to do is transform the x parts by using this. So we'll be using cos of theta there. And let me get this one right. Cos of theta and sine of theta. Yeah, okay, sine of theta. And then this one is going to be put in here. So that's minus sine of theta, and that's cos of theta. So when you're multiplying that out, you can see that you will get cos theta times by your x there. So you're going to get cos, that's right, x cos theta, x cos theta, and then you're going to get minus y sine theta, and then you'll get, again, the sine applying to x there in the y direction. That's what's happened to the x component in the y direction. So this is going to be our y direction here in our final coordinate point. Here's x, here's our new y. And so we're going to get x sine of theta and then plus y cos theta. Now, this thing here, this final thing here is what you're going to be making. That's not given in the formula booklet. Only this is given in the formula booklet. But that's ultimately what's going to come out. Okay, so, in the x direction, we'll get this 1, 0 will have the new x component of cos theta, but likewise there will be a new x component to this y height here as well, because that will now move around and have a new x component as well. So that new x component is going to be this. So we need to apply the the minus sine of theta on the y to get the new x component here. Hopefully that's making some sense. Okay, so that's how we developed this formula. And this is your rotation. This one here is rotation by theta degrees, and that's anti-clockwise. So theta degrees, anti-clockwise. Okay, oh, and also should be noted that it's about the origin. So the center of this rotation is always 0, 0. We're not using any other centers of rotation. Okay, now that was really similar, of course, to when we said about having 90 degrees. Now, if we did have 90 degrees, remember cos of 90 degrees, cos graph, it's like this, cos of 90 degrees is 0, so you get 0. Sine of 90 degrees is 1, so you get minus 1 there. And sine of 90 again is 1, and cos of 90 degrees is going to be 0. So we get this as your rotation by 90 degrees anti-clockwise. So that one would be your 90 degrees, and you'll have to work that out yourself. Okay, now obviously you could do the same thing by going clockwise, but I'm not going to do that now. We've done that, we've developed that formula, you just need to apply that in later examples now. Okay, but there is one thing which is outstanding at the moment, and that's the first one which they came up with, which I think is actually the hardest one to develop, which is this reflection in the line of y equals tan theta x. So now let's take that. So we're trying to develop this formula here. And again, obviously you can just apply the formula, but I expect as higher level students, you probably want to know where these things come from. Okay, well, let's just set this up in terms of an x component to start off with. So again, let's set this up in terms of 1, 0 here. And we're going to set up this line, which has got alpha here. Alpha? No, let's not take alpha, let's take theta. They're using theta here. And let's do a point to the line here. Let's take this line up to here. By the way, this now has the gradient of tan of theta x. And remember, tan of theta comes from your TOA triangle. So tan of theta is actually equal to your opposite over your adjacent. And of course, that's just your gradient formula. Opposite over adjacent is your opposite, is your adjacent. That's just rise over run. Okay, so that's the same thing, rise over run. So that's why they've got it in this format here. Because if you're told what a gradient is, then you can easily know what tan of theta is as well. You know, you can find out what theta is from the gradient by, if you know what the gradient is, then the gradient is, say, for example, a gradient of 2 would be a rise of 2 and a run of 1. And then you could work out theta by doing inverse tan. Anyway, that's a different question. So in terms of reflecting this this cross here, that's going to take us somewhere over here. Right, somewhere up here, okay? So if we go to the line and then across the line, that's going to be at right angles. Now, in terms of that coordinate point, that's going to create a right angled triangle here, which has theta here, but also theta here as well, because that's our reflection. You can see here that we now have a reflection. We have the same angle on this side and the same angle on this side as well. Okay, so we also know that this is a length of 1. And in terms of taking this coordinate point and making this coordinate point here, we can see that we now have 2 theta as our angle here. So this overall angle is now 2 theta. So that's going to give us our coordinate point of an x distance across, just like before. We're going to use cosine in this triangle here, with this as 1, with the angle in the corner as 2 theta. And so then you're going to say, well, this is going to be, the adjacent is going to be cos of 2 theta there. And the opposite length, which is going to be the height, is going to be sine 2 theta. Got the hypotenuse, we're looking for the opposite, so we'll use sine of 2 theta there. Okay, so in a similar way to before, our 1, 0 is going to become cos 2 theta and sine 2 theta when we shift an x component of any coordinate point by reflecting it around a line of y equals mx or y equals tan theta x. Okay, and just like with the rotations, we need to do this with the y coordinate as well. So I'm going to attempt to do this with the y coordinate. I'm just going to use the space down here. And this one is perhaps a little harder to see, I think. So again, I'm going to try and make this, and I'll make this one here, and I'll put a theta here. So there's our theta. And then I'm going to use this coordinate point up here. This is going to be our coordinate point 0, 1. And then, of course, we're going to the line and across the line as well. So we're going to end up somewhere over here. Okay, and there's 90 degrees on both of those points there. Obviously, those lines are perpendicular to our line that we're trying to reflect about. Okay, now it's not too difficult to show that this is also going to be theta up here. Okay, so if this is a right angle and this is a right angle, and say, for example, this was going to be 90 minus theta, then this also has to be 90 minus theta, and then therefore this is also theta. So these are two similar triangles here. And likewise, on this side, you'll also see that we're getting theta here. That's just the symmetry that we're seeing there. Now, a little bit more than that, in that we also know that this angle here, given that this is an alternate angle, this is also theta. So that's theta, and hang on, that's theta as well, because it's the same as this one. Now you can see, again, we've got 2 theta there. So again, this total angle is going to be 2 theta. So we've got 2 theta here. We know we've got a length of 1 here again. So that's just the same as this length of 1. So we've got a length of 1. Now we've got this right angled triangle here. Okay, so now if we want this length here, so our distance across, that's now sine of theta, or sorry, sine of 2 theta in that right angled triangle, in this right angled triangle, the yellow one. So our new coordinate point down here, okay, is going to be sine of 2 theta there. And then, of course, the distance down is going to be cos 2 theta. But because it's down, we're going to need a minus on that one as well. Okay, well, we're nearly there now to create the total reflection. So if we combine these two things to act on a particular coordinate point, then we're going to have the cos 2 theta and sine 2 theta acting here. So cos 2 theta there, not a comma, sorry, and then sine 2 theta is acting there. So that's what's happening to the x coordinate point here, and we're developing out. That's not, is it? That's what's happening. That's the x part. The cos 2 theta is the x part, new x part from the x component there, and this sine of 2 theta is actually coming from here, isn't it? We're doing sine 2 theta acting on the y there. So that's the new x component that's coming out from acting on that y component there. And then, of course, the other part is sine of 2 theta. So that was x and x acting on the x, both of these things here. And then, of course, our final part, finishing this off, is cos of 2 theta there, minus cos of 2 theta. So this is now giving us our reflection matrix about a particular line which goes through the origin. So there's no extra plus c there. This is a matrix transformation reflection about a particular line which goes through the origin. I'm not going to multiply this one out, but hopefully I've shown you how to get that first formula at the top there. Okay then, guys. Well, that was some tricky stuff. What I really think that this investigation here is excellent. So I would go through this and go through this carefully and write notes as you go as well, of course. But this is a good investigation. It's basically the stuff that I've just gone through. Now, example 7 and example 8, I'm going to leave for the time being, but these are good ones. These are good ones to do, and they're obviously an application. In terms of example 8, they're talking about that this is slightly different. It's saying find the 2 by 2 matrix that will transform the point 2, 1 to 1, 4 and the point 1, comma minus 3 to 4, 9. And in fact, they're doing this by setting up simultaneous equations. So if you don't know what the matrix transformation is, it's possible that you can have more complicated combinations of matrix transformations. Sounds like something's burning in the kitchen. That sounds like time for me to stop. Okay, guys, thanks for listening in, and I'll go through the examples next, but good luck with the investigation. Good luck with the exercise if you decide to just plow on with that straight away.